Okay, we're talking about continuity some more today. Continuous functions and points where it's continuous, points where it's not discontinuous. In my sort of brief introduction last time, I will just refresh your memory about the definition. Continuous at some point x equal a means, it means that the limit as you approach that point along the curve, lim x goes to a of f of x. This means as you travel along the curve towards a, what the answer that you get is, the y value you get is actually equal to the y value right at a. This is a very technical way of saying basically where the curve goes to is where the points are also. There are no points that are sort of bounced off of the curve for some reason. All right? The picture you should have in your mind is just sort of the curve kind of does one nice little thing without any breaks in it. They say you can draw the curve without lifting your pencil. All right, that's what it means to be continuous. And if I show you the graph of a function, you can easily tell me immediately if it's continuous or not. This one is continuous. Something which is not continuous would look something like maybe it has a gap in it somewhere. Whoa. Something like that. This is not continuous because it has a point missing on the graph. And that, such a point, like in this case, maybe it looks like it's at x equals 1. If I saw that point, I would say x equal 1 is a discontinuity point. That's the fancy language for that, all right? A discontinuity point is one where, for some reason, this definition that I said up here is not true right there. Now, in this particular example, the limit of the function actually does equal 2 right here, but the actual value of the function does not exist. So this equation is not true, because the right-hand side isn't even a thing at all. The left-hand side is 2, which is fine, but the right side is nothing. There is no f of a in that case. All right? Such a point is called a discontinuity point. So, easy to tell if you're looking at pictures. What I want to talk about today is what if I don't show you the picture, but I just give you a formula for a function. Can you tell me, is it continuous or not? And if not, what are the discontinuity points? All right, that's what we're looking at today. So, finding discontinuities. On a graph, it's easy. On a formula, you have to sort of look at the formula and know what to look for. All right. Fairly straightforward example would be something, I just want to do a few examples. Let's try something like x squared minus 2x minus 3 divided by x minus 1. This is an example. Find any discontinuities. All right. What we have here is a rational function. That is, it's a fraction with a polynomial on the top and a polynomial on the bottom. Everybody knows that polynomials are continuous. When you look at the graph of a polynomial, it doesn't have any weird holes in it or anything like that. It doesn't have asymptotes or jumpity jumps. The only thing that really should concern you about this formula in terms of continuity is the fact that it has a denominator there, and this automatically does not exist when the denominator equals 0. So if you see a formula like this, a rational function, what you should immediately zero in on is we need the denominator to be non-zero. Because when the denominator is 0, then automatically this function value does not exist, which means there's going to be a hole in the graph. And so that will be a discontinuity point. So for which x's will the denominator be 0? The denominator is 0 when, what do you want to say? Shout it out. 1. Yeah, somebody gave me the finger. Not the finger. 1, right? When the denominator is 1, the denominator will be 0 when x is 1. So in this example, you can just sort of look at that, and you can tell that x equal 1 is going to make the denominator 0. In a more complicated example, you might have to like separately set the denominator equal to 0 and then solve for x to figure out when those sort of bad points will be. This is like a bad point because this is a point at which the function is not continuous. But for all other values, this function is continuous, all right? So the denominator is 0 when x equals 1. So we can say this function, I never gave it a name. I'll give it a name over here. So f of x is continuous. There's a few ways that you could sort of phrase your answer. I would say f of x is continuous for all real numbers except 1. Right? 1 is the only place where something weird happens with this function. At all other points, it's just like a polynomial, which is totally fine in terms of continuity. All right? So f of x is continuous for all real numbers except 1. Another way to say that, I suppose I didn't specifically answer the question, says find any discontinuities. So if I really wanted to answer exactly that question, I would say x equal 1 is a discontinuity point. Discontinuity. All right. Those are basically two ways of saying the same thing, right? Any thoughts about that one? This is fairly straightforward if it looks like, a fraction involving polynomials on the top and the bottom. Okay, what about, here's a slightly more interesting kind of example. What about a piecewise function? Here's a new example. How about this? F of x is 3x squared minus 1 if x is less than 2, and x plus 10 if x is greater or equal to 2. All right? Is this one always continuous, or does it have any discontinuity points? The fact that this is in two pieces, you can kind of, it's hard to say exactly what the graph of this looks like, but you can kind of imagine the graph. The first piece looks like a parabola, and the second piece looks like a line, right? So the graph of this, and it kind of transitions from one piece to another over here at x equals 2. It looks something like you have a parabola part, which is kind of steep because of the coefficient of 3, I guess. Something like that for the parabola part, and then it suddenly at x equals 2, it becomes a line. And I suppose because of the way the less than and the greater or equal is, it's something like that, right? It's a parabola to the left of 2, and then it becomes a line to the right. Now, I drew the picture like that, but actually, it might be that the line part is up here, or it might be, by some coincidence, the line part actually goes right there, all right? It's like one of those, it's not clear exactly which of those three lines it is. I don't mean it's all three, I just mean one of these lines, all right? It's not exactly clear which of them it is. And if the question is, what are the discontinuity points? And then actually it matters. Like if it is really the line in the middle, then it really is continuous there. If this curve really sort of meets up at this point, then it would be continuous. Whereas if it's one of these lines up here or down here, then the curve is not continuous at that point. So this is sort of what we need to check. We need to check, I'll say this kind of in vague terms, we need to check if the pieces meet up, right? If by some kind of magic they actually meet up at the same point, then it will be continuous through that point. But if the pieces are misaligned, then it will have a discontinuity, in this case at x equals 2. Anyone want to suggest how we could check that? Do the two pieces actually meet up at the same y value there? Yeah. Yeah, we're going to plug in 2 for both pieces. Now, you might look at this and say, well, you're not supposed to plug in 2 for this piece. You're only supposed to plug in 2 for the second piece. But that doesn't matter. We know the actual value at 2 is given by the second piece. But I want to know if the two lines meet up. And the way to do that is to test out by plugging this value into each of them. So I'm going to plug in x equals 2 for each one. and see if we get the same answer. Really, that would give me the y values for this point. Either they're going to match or they're not going to match. Let's try it out. So if I use the first formula, I get 3 times 2 squared minus 1, right? This is 3 times 4 minus 1 is 11. And if I use the second formula, I get 2 plus 10, which is 12. They do not match. In fact, apparently this means the line is higher up than the parabola at that point, right? The parabola goes up to 11, the line goes up to 12. So really, it really does look something like this one here. All right. Anyway, what do you say? Is it continuous or not at that point? It is not, because the thing actually jumps up at that point. So these two numbers are different. I'm comparing those two. So these are different. So f is not continuous at x equal 2. All right? It is continuous everywhere else, because x equal 2 is the only place where something weird is happening. At all other points, it's either a parabola or a line, so it's automatically continuous everywhere else. All right? Any questions about dems? This is really what you need to look for if I show you a formula and ask you when it's continuous. What you want to look at is 0 in the denominator, and you want to check if pieces match up, if it's a piecewise. All right? It's not a piecewise, we don't care about the pieces matching up. All right? So I'm going to say, generally speaking, if there's no denominators or pieces, then it's basically always going to be continuous, right? If you don't see any of this weird stuff that might happen, if there's no denominators or pieces, it will be continuous. I'll say on its domain. More on that in a moment. But generally speaking, when you look at a function, if you are asked to find where it's continuous and where it's not continuous, what you should look for is denominators being 0 or pieces which may or may not meet up. And you have to check those. All right, so for example, e.g., polynomials, things like sine and cosine are all continuous everywhere. Everywhere. All right? They are continuous for all real numbers, because there's no funny business. I mean, we all know what the graph of sine and cosine look like. They have those nice curvaceous curves, which they don't have any holes in them or anything. So sine and cosine are continuous, and polynomials the same way. All right? Sorry, my pages are out of order here. I'm going to say something about, so a similar question, which really does not involve any new ideas really, but sometimes in the book the question will be asked like this. Sometimes they ask for, sometimes they say it this way: give me intervals where this function, how about f of x equals x plus 5 over x squared plus 4x minus 5. Give intervals where this is continuous. All right, we can do that. It's more or less, I mean, the same kind of thing that we've been talking about so far, but sometimes they ask you in terms of intervals where it is continuous. Anyway, you try and think of it in the same way. I look at that and I say, I don't like the denominator, right? The denominator could be 0. So I'm going to check when the denominator is 0. When will the denominator be 0? Now, in this example, it's a little hard to just look at that and guess when that will equal 0. For which x values do you get 0 in the denominator? So if you don't like guessing, which I don't, you can write it this way. And then try and solve that for x. How do you want to solve that for x? Yeah, what do you say? Yeah, this you should factor. I suppose you could use the quadratic formula, but I'm not really into that if I can factor instead. Yeah, factor like that, and then, you split it up. X plus 5 is 0. X minus 1 is 0. So, -5 and x equals 1. All right? I put a box around it. That's not my answer, though. I mean, that's not the answer to the whole question. The question was, give me intervals where it is continuous. Actually, those are the points where it is not continuous, right? So if I want to say where it is continuous, it would be all real numbers except for those 2 points. But if it specifically says, give me intervals, so I will say it is continuous on the intervals. Can anyone express this in intervals? I want to say everything except -5 and 1, but say that using intervals. What do you think? Uh-huh. Yes. Uh-huh. Yeah, great. So it is continuous on those intervals. And I'm using the roundy parentheses to indicate it is continuous. For example, right here, the roundy one, that's supposed to be a roundy one. It looks a little ambiguous. I'm going to make it extra roundy. This one here, the fact that it's rounded on this side means that it is not actually continuous at x equals -5, right? Continuous for all the numbers up to, but not including x equals -5. Excellent. These are the intervals on which it is continuous. Some people want to be fancy. You can write it this way. -∞, -5, union, -5, 1, union, 1 to infinity. That's great too. You want to say that. The union is an operation for intervals, which kind of means you take all of these things together, right? Excellent. Any questions about that one? Okay, one last thing to be concerned about for things like this. Here's one last example. I think these are fairly straightforward. Again, same question, give intervals where it's continuous. And I am referring to this. How about this? Square root x plus 3 divided by x minus 10. Welcome back. The square root introduces a little sort of extra technicality that you have to worry about in this case. As always, we are concerned about the denominator. We must make sure the denominator is not 0. But also, we have to be sure that the thing inside the square root has to be positive, right? This is how square roots work. So the two things to observe here are denominator must be non-zero, and the inside of the radical, the inside of the root, must be positive. All right? And you have to sort of consider both of those things together. Okay? Just consider them, one at a time. The denominator must be non-zero, so denominator equals 0 when, in this case, you can just look at it and tell. The denominator is 0 when x equals 10. So it is not continuous when x is 10. And then also the inside of the root, we need, so I'm going to say it this way, x cannot be 10, right? For it to be continuous, x is not allowed to be 10. And also, we need x plus 3 to be positive, right? Actually, greater or equal to 0. That's the inside of the square root. And we can kind of solve the inequality for x, right? I would just subtract 3 to the other side. So we would say x is greater than or equal to -3. All right? So as far as where is it continuous, I would say it is continuous for all numbers that are greater than -3, except 10. It's not allowed to be 10, but it can be anything else as long as it's greater than -3. All right? So I will write that, although that's, really my answer is supposed to be expressed in terms of intervals, but just in words, I'm going to say it's continuous for every x which is bigger than -3. Whoa. Except x equals 10. Right? And anyone want to say that as intervals? What do you think? Yeah. Huh? Yeah, great. So he said union. Even better. I'm going to say union. Great. Actually, there's one slight thing I would change about that. Yeah, it's the closed bracket on the 3 because of this, greater or equal to 3. So technically, it should be that. Yeah, great. Any other thoughts about that? This is how you say where it's continuous as intervals. Excellent. All right. I'm going to talk a little bit abstractly. My clock on the iPad is messed up. About rules for continuous functions. You can combine together continuous functions and make more continuous functions, like by adding them together or multiplying them by one another. So this is sort of simple rules for continuous functions. We're not going to go through like proofs of all of these, but actually they're pretty straightforward. They follow immediately from the laws for limits. Remember the limit laws, which said like if I have the limit of two things added together, that's the same as the limit of the first one plus the limit of the second one. Since continuity, the definition, is based on a limit of something equals something, you can use all those rules about adding up limits and sort of translate them into rules about what happens when you add together two continuous functions. And it says this, I'm just going to write this as a big theorem. If f and g are two continuous functions, then you can add them together and the result will also be a continuous function. That's the first thing. I'm going to say many things, but the first of them says then f plus g is continuous. If you have two continuous functions and you add them together, the result is also continuous. So, for example, this is how you know, if I asked you, how do you know that something like x squared plus 7x plus sine of x, that's continuous, right? Now, it is continuous. If you ask me, why is that continuous? Well, I can't exactly say, well, because it's a polynomial. It's not a polynomial because it has that sign on it. But it is a polynomial plus the sine of x, and each of those things by themselves are continuous, which means that the whole thing is continuous, according to this rule here. If I have two functions which individually are continuous, and I add them together, the result is continuous, all right? This is continuous. Yes. Okay, anyway, what else can we do to combine continuous functions and make a new one? You could also subtract. That's basically the same as adding from a certain point of view, right? You could also even multiply the functions together. F times g is continuous. Basically, all the ordinary ways that you would want to combine two functions together, it'll work, and you will get a continuous result. Another thing you can do is just take one function and multiply it by a constant. That will still be continuous for any real number. Real number C, all right? And you can divide, but as usual, there's a little caveat. F divided by g is continuous. Whenever g is not 0, right? If the g is 0, you know, you have to check when you see a fraction like that. You always have to check if the denominator is 0 or not. But if for those points at which the denominator is non-zero, then the fraction f divided by g is continuous. All right. I've actually been using these rules all along. For instance, when I looked at something like, you know, x squared minus 1 over x plus 3, I said the top and the bottom are already continuous. All we care about is when the denominator is non-zero. For all the other points, it's all going to still be continuous. That's actually, I was using this rule here, that this thing, because it has two parts which are individually continuous, the whole thing will be continuous as long as the bottom is not 0, right? Which is how we've been doing it all along. So these rules really, we have been kind of assuming them throughout. I hope you didn't mind all of that. All right. One other important way in which you can combine two functions is to plug them inside one another, like so. This is called the composition of two functions. You stick one function inside of another function. And it's still true, this is continuous. This is how you would get something like sine of, you know, x squared plus 3. That is still continuous because it's a polynomial stuck inside of sine. And the sine is continuous, and the polynomial stuck inside is continuous. Means the whole thing is continuous. All right? These are rules about continuity. Any thoughts about that? You don't, like I said, we have been kind of implicitly using these rules all along for the past 20 minutes or so. So you usually don't even really have to think about the rules. Although if you want to be very specific about what you're talking about, you need to mention the rules every so often. Like here's just one last example. How about, where are the discontinuities of tan x times x minus 1 over x plus 2? That's multiplication right there. I said all along that sine and cosine are continuous. I didn't mention tangent. That's because tan actually is not always continuous. I hope you remember what the graph of the tangent looks like. It has a bunch of asymptotes in it, right? Remember? It looks like this. This is the graph of tangent, something like that. And every one of these is an asymptote. And those are points where the function is discontinuous, right? Because you can see the line breaks there. Anyway, what we have here is two functions multiplied together. And because of the rules I just said, if you want to say, when is this whole thing, the multiplication, discontinuous, it suffices to just look at the two parts individually. So what I'm going to do is look for discontinuities of tan, and then also look for the discontinuities of that fraction part. Actually, the fraction part is a little easier. Can we do that? So the discontinuities of the second part, x minus 1 over x plus 2, are, anybody say, what are the points at which it's not continuous? Negative 2, yeah, that's it. Just when the denominator is 0. That's the only discontinuity point of the second one. Something you've noticed already, I think, although I never said it, but the numerators really are totally irrelevant here. And it even doesn't matter if the numerator has a factor that cancels with one of the denominator factors, it still counts as a discontinuity, even if the factor can cancel. Anyway, so that's one discontinuity point. And then I also look at the discontinuities of tan. Discontinuities of tan x. Now this has many discontinuities, infinitely many. You can see them on the graph. Maybe you just have sort of memorized where these discontinuities are. If you don't remember the graph, you could also, it's usually a good idea to think of tan as sine x over cosine x, and think about when is the denominator going to be 0 there, right? So this has a discontinuity whenever cosine x equals 0. Any masters of trigonometry? When is the cosine equal 0? There's a few hot angles that you could just guess. Yeah? Yeah, 90 degrees, also known as pi over 2. That's this one, right? And then these other ones would be shifting that by pi, by 180. So this is, yeah, it's because, remember the graph of cosine? It looks like this. Or this is pi over 2. This is 3 pi over 2, right? 90 degrees, and then whatever, 90 plus 1, 270, right? And so on. The next one is, I don't know, whatever 180 plus 270 is. I'm not a skateboarder. I don't know those. Anyway, what are the x's then? So I'll say this in radians. I'll say i.e. Pi over 2, I'll just say it this way, plus pi n for any whole number n, all right? Or in degrees, you could say 90 plus 180 times n, or any integer n. All right, so what's my final answer? What are the discontinuities? It's sort of these together. So this is a discontinuity, -2, and also all of these are discontinuities. So just to summarize here, I've already done all the work here, but the discontinuities are -2 and all these other ones, pi over 2 plus pi n. All right. All the discontinuities for tan, and then additionally -2. Any questions about that? I hope that seems to make sense. You'll have some more practice with those on the homework. All right, what do we got? We got 15 minutes? Great, I think that's enough time to say what I wanted to say. Maybe not, we'll see. The last thing to say about continuous functions in this section in the book, you know, this section is all about continuous functions. I want to talk about one very important theorem about continuous functions. You may be familiar with this. This is called the intermediate value theorem. The intermediate value theorem. There's a few different value theorems in calculus. This is maybe the simplest one, and it's one that I think the basic idea of the intermediate value theorem is something which is obvious to most people. Like even a kid will understand what the intermediate value theorem is. They probably wouldn't understand the way that we're about to explain it, because I'm going to say it in a technical way, but the basic notion is something that I think every person is familiar with. I'll say it very vaguely first. If a continuous function goes through two different y values, then it also hits all y values in between. All right, this is a vague way of saying the intermediate value theorem. If you have a continuous function, it must be continuous in order for this to be true. If you have a continuous function and it goes through two different y values, that function also goes through all the y values in between. Well, here's a picture to demonstrate what I'm talking about here. By the way, this y values in between, this is the name where it gets its name. These are the so-called intermediate values, right? That's why it's called the intermediate value theorem. Any in between, that's, intermediate meaning in between. Anyway, if I have a function, say, looks like this maybe, and I say if it goes through two y values, maybe here and here, I'll call these points A and B. And this is, of course, f of A, and this is f of B, right? So this function goes through the y value f of A, and also through the y value f of B. What the intermediate value theorem says is that it must also hit all the intermediate values, that is, all the other values in between. So if I were to choose another value somewhere in between, maybe this y value right there, Is there a place where the graph goes through that y value? Well, I mean, yeah, there is. It's right here, right? And there is an x value, actually, so that when you plug it into the function, you get that intermediate y value. And that's true for any choice of value in between f of a and f of b, all right? This is why, for instance, like, right now I am, I am something like 6 feet and 5 inches tall. That's how tall I am. And would you believe it if I told you that I was, at one point in my life, I was exactly 3 feet tall? The answer is yes, you would believe it. Why would you believe that? Basically because at some point I was like 0, I was nothing, and now I'm 6'5". At some point in between I must have been 3, all right? This is what the intermediate value theorem says. It says if you have two values and the function is continuous in between, then it has to actually meet all of the in-between values at some point, all right? That's why, this is why I said, I think this is something that even a child understands the basic concept, and it's something that will seem obvious to everybody. It is true of any continuously varying quantity in the real world, right? Okay, anyway, let's try and state this like in more formalized language here. And I hope you agree that the continuous, it is really important that this function be continuous. If it were not continuous, then the theorem might not be true. For example, if it were not continuous and my function did something like this, right? And then if I looked at, say, two values here and here, so I'm making the same colors here and here. Here's f of a, and then here's f of b. So this function is not continuous. It does go through f of a and f of b, but I think you can see there's like a gap of y values which it never goes through, right? But that's because the curve actually jumped over those values. We're saying if the curve is continuous, meaning it cannot jump over any values, it has to go through all the intermediate values, right? So the continuity is really important. Anyway, here's a real sort of formalized mathematical statement of the intermediate value theorem. It says, let my function f of x be continuous on the interval a to b, and let n be any number between f of a and f of b. This is the intermediate y value. So on the picture, the n is here, right? That's the n. N is some chosen number in between the two y values. And I've assumed that f, the function, is continuous on the interval from a to b. It really doesn't matter what it does outside. It has to be continuous in between the two, inside the range that you're looking at on the picture. Let n be any number in between f of a and f of b. Then, what I want to say is, then this number n actually appears as a y value on the graph in between a and b. So the way to say that technically is, then there is some x in between here, which is like this value here. There's some point along the x-axis where actually you do really get n as the y value there. So I'm going to say there's some x that's in between a and b. So a less than or equal to x less than or equal to b, with f of x equals the n. The y value at that specific point actually equals the in-between y value on the graph. Sorry, my picture is so far away from my words there. All right? This is the technical statement of the intermediate value theorem. Any thoughts about this? This is there are various sort of contrived real-world uses of the intermediate value theorem. This is sometimes, I've heard the intermediate value theorem described like if you're out to dinner with somebody and the table is like rickety, because the legs are not perfectly balanced. Maybe the table wobbles from side to side. There's a way to demonstrate sort of mathematically that there is some way to stabilize the table by turning it. Because if it wobbles, say, from left to right, if you turn it all the way around, like 180 degrees all the way around, then the wobbling will have been exactly reversed. I think I'm misremembering this scenario. It's not a real thing. This is like something that mathematicians like to talk about when they're nervously having dinner together and don't know what else to talk about. Yeah, I should probably just stop the analogy. Let's just do a mathematical example here. I'm going to have to do some more research on that wobbly table thing. I thought that I remembered the story, but as I was telling it, I realized I didn't actually remember the story. Let's do a specific example. We got enough time for one of these. You can use the intermediate value theorem to demonstrate certain weird properties of various functions. So let's do, how about this? Show that there is some x with sine of x equals, I'm going to write a very specific value. Like everybody knows, sine of x equals 0 for certain values, it equals 1 for certain other values. I would like to demonstrate that there is some x, which sine of x equals 0.8675309. Remember that song? All right, can we explain why this must be true? Actually, it is true. There is a value of x. I don't really know what it is, but there is a value of x for which the sine of x equals that very specific number, Jenny's number. All right? And the idea here is we're going to use the intermediate value theorem. So the function that I'm going to use is sine x. So let me just start by saying sine x is continuous, so I can use the intermediate value theorem, right? If it wasn't continuous, you wouldn't be able to use intermediate value theorem at all. So we can use intermediate value theorem, all right? The idea is I would like to somehow demonstrate that this is a value which is in between two other values which I already know about. All right, so what you have to say is something like 0.8675309 is in between, so we need to say that this is in between two other values of sine x. And you know, we would like to be able to say specifically what the two other values are. Anybody think of this? So you need to think of sine of something equals some specific value here, and then sine of some other point equals some other specific value where the 867 whatever is actually in between those two answers that you get. Can anyone think of two values of sine x which have, you have to be, I suppose, very slightly creative, although not super creative. Yeah. Yeah, everybody knows, like, sometimes the sine equals 0, and sometimes it equals 1, right? So I actually primed you for that answer, because I just said those words exactly a few minutes ago. I'm going to try to choose some value. And can you give me specific x value? This may happen more than once, but all I need is one specific value. What is an x value here that makes sine of something equal 0? Yeah. 0, yeah. So I'm going to put 0 here. And how about the other one? What makes it 1? Pi over 2. Yes, thank you for the radians. I'm into it. Yeah, remember the graph of sine? It looks like this. Or this is pi. This is pi over 2. All right? So what we have here is, you know, in the picture of the intermediate value theorem, this is the f of a, right? And this is the f of b. And this is the b, and the a is the origin. All right? And my number, this Jennings number, is in between. It's like around here somewhere. And it is true, there has to be some x value down here. So let me just try and summarize here. I'm going to say since 0.8675309 is between 0 and 1, that means there is some x value. In fact, we can be kind of specific about where the x value is. Like you can tell on the picture, it's going to be between 0 and pi over 2, right? I can't say more specifically than that. But there is some x value. Can I just say in the interval 0 to pi over 2 with sine x equals this number, this ridiculous number, 5309. All right, this is the intermediate value theorem. All right, and I think we got 2 minutes. I want to do one more example of these, but we can start that off next time. All right, that'll do. Send in those homeworks. I'll hang around if anybody has homework questions. I'd be happy to chat for a few minutes about it. And tell me your grading choices.